Okay, guys, so today we're gonna start a new chapter. Basically, in this chapter, we are going to connect the kinematics of rigid body motion with the forces and moments or torques that are applied, and then we are going to introduce the concept of torque. I just want to do a brief recap from chapter 17. But this is again chapter 18, and a quick recap basically regarding rolling motion, because this is going to appear with us throughout this chapter. We said if you have a wheel that is rolling that is in rolling motion where there is no slip, right? What we would like to do is basically we would always like to find the acceleration of the center of gravity, right? And we are going to use the acceleration of the center of gravity in this chapter 18 to basically find the acceleration from the forces, or we can have the forces and then we are going to be able to find the acceleration or the angular acceleration of the rigid body from the external forces which are applied. Just a quick recap, guys, on the kinematics of rolling motion. If you have a wheel, what is the acceleration? Let's say I have point O, and I have point G, and let's say I have point A over here. Can someone tell me what is the acceleration of point O? You probably need to know a bit more information, right? Like if I have alpha
Zero.
Let me do something. So let me assume that this rigid body has angular acceleration in that direction, and it has omega in that direction, right? This is omega. The acceleration of point O, if you remember, right, from one of our previous lecture, it was equal to this guy, omega square times r, right? Where r is the radius of this disk, right? How about the acceleration of point G? So if there's no slip, just like what we said last time, right, you would have alpha r like that. And these are the magnitudes, basically, of these acceleration vectors, right? Let's say I would like to find the acceleration of point A. How do I do that? So I'm going to have to apply the equation, and essentially we are going to use this kinematics to be able to find the acceleration of any point, including center of gravity. In this case, it's a simple problem. Basically, we have the acceleration right here at the center, but we are going to be using those throughout the next chapter to be able to find the acceleration of any point. So if I want to find the acceleration of point A, I could use point O as my reference, or I could use point G as my reference. If I use point O as my reference, first of all, I'm gonna write the equation: AO plus alpha cross RA with respect to O plus omega cross RAO, which is equal to omega square RAO. So all that I have to do, basically, in the case always a wheel that is rolling with no slip, you have this acceleration of this point. It will always be like that. So I'm gonna, since using the acceleration of point O, so I'm gonna basically take this guy and then put it here. So I'm going to have omega square r. So now if I actually use point G as my reference, then I'm gonna start with alpha r, right? So I would replace AO with AG, and then I'm gonna begin by putting alpha r like that. So this is the acceleration of point O. Then next step is alpha cross RAO. How do you think this vector is going to look like if I want to draw it? Well, this guy is RAO, right? This guy here is RAO. So alpha cross RAO is going to be a vector like that, right? So it's going to be following this alpha. Okay, so it's going to be a vector that is perpendicular to here, right? And what is the value of this vector? It's simply equal to alpha multiplied by the length of RAO, right? So if I have here R and then R, this guy is going to be R times square root of 2, right? So the value of this vector is going to be alpha square root of 2 times R, right? So this is that component, and then the last one is going to be equal minus omega squared RAO, which is doesn't matter on the sign of omega. It could be in clockwise or counterclockwise. You will always have your centrifugal acceleration as omega squared RAO. What is the length of this vector? It is, this guy is 45, so it's going to be square root of 2 multiplied by r, right? Now, if I want to actually write the magnitude of this acceleration of AA, right? So what do I have in the I direction? Let me put that frame very quickly here. What am I going to have in the I direction? So I believe this angle here is going to be obviously 45, right? Then this angle here is 45, and then this guy is 45, right? So the acceleration of point A, so starting off in the I direction, I'm going to have this guy, maheke, so minus alpha, the square root of 2r, multiplied by cosine 45, right? Which is basically square root of 2 over 2. And this guy also is it is the same thing, so minus omega squared, the square root of 2r cosine 45, which is basically the square root of 2 over 2, and then this is I. So in the I direction, basically all the vectors are pointing in the negative direction. And then how about in the J direction? So in the J direction, basically, first of all, I have omega squared r, so this is purely in the J direction. How about this guy? So this guy is plus alpha square root of 2 r times sine 45, which is square root of 2 over 2. And then the last one is basically minus, so minus omega squared times square root of 2 r sine 45, which is square root of 2 over 2, and then this guy is j. So I can rearrange this, and square root of 2 multiplied by square root of 2 will be 2. So this guy and this guy is actually equal to 1. This guy is equal to 1. This guy is equal to 1, and that guy is equal to 1. So it actually simplifies very quickly. So minus alpha r minus omega square r in the I direction, and then in the J direction I have omega square r minus omega square r. It will actually cancel out, so I'm going to end up with alpha r j. So in the J direction I actually simply have alpha r, and then this guy is going to be what I have in the I direction. All right, guys, any questions on how we do this, or how we find basically the acceleration at any point? So you can do this, or you can basically do the cross product and then extrapolate them and then find your I and J components, and that would be it. So the idea here is we would like to always find the acceleration at the center of gravity. Okay, so this is very good. Now we can actually start with the real chapter 18. And in this chapter, basically, and this is really one of the most important chapters that we have in dynamics. And you understanding this is actually very important to you, in this course and also down the road, to be able to analyze dynamic systems, finding the forces, finding the accelerations of any points. So here's what you have. So what we are going to do is, let's say I have, this, random rigid body. And that rigid body essentially is going to be subject to a bunch of forces, right? So I could have, F1, I could have another force like that at this point, basically, and then that force is F2. I could have another force here, F3, right? So this rigid body could be like, sitting on the plane, and you have, a bunch of forces applied on it. These forces actually have to be equal to MA. And here's what we'll do. So the same rigid body, basically, right? So, first of all, you obviously have to identify the center of gravity of that rigid body. And I'm going to actually put it on both. So this is the same rigid body. This is my G. And these forces have to be equal to one acceleration vector, right? Or MA, basically. So here's what I'm going to do, basically. I'm going to have this vector is my mass times the acceleration, right? So, and obviously you are going to have this IJ frame, all right? So here's what is going to happen. So if I sum the forces on that rigid body in the X direction, right? I'm going to get what? So I will basically sum these forces, and these forces actually have to be, so if I'm summing the forces in this direction, so they will actually have to be equal to M A, right, the acceleration of the center of gravity, so magx, right? So summing the forces in that direction, you basically have to sum these forces, and then these have to be equal to that. And then if you sum the forces in the vertical direction, they actually have to be equal to agy. All right, so you take, if you're summing the force in x direction, you take this x component of that force, right, which is, this, the x component of that force, which is that, and then the x component of this force, which is in this case its opposite, have to be equal to magx. So from the forces, you can actually find the acceleration, but of what point? So if you sum the forces, you can actually only find the acceleration of the center of gravity. All right. So from these forces, you can actually find the x component of the center of gravity. Summing the force in a vertical direction, you can find the acceleration of the vertical acceleration of center of gravity. If you want to find the acceleration of that point on a rigid body, let's call it P, you actually have to use kinematics, right? You won't be able to use the forces to find the acceleration of a point that is not the center of gravity. But how do we actually use these forces to find the acceleration of that point P? What we have to do is basically we have to find the angular acceleration of that rigid body. Here's what happens. So that rigid body actually, so at the center of gravity, we actually have ma, and every rigid body, it has this mass, right, which is a property of the rigid body. It actually has another property, which is called rotational mass, which is the moment of inertia. So what you are going to do is basically you are going to add this guy, which is Ig alpha. And Ig alpha is like the rotational mass of that rigid body. Ig is called the moment of inertia of that rigid body. In this case, it is a planar moment of inertia, and Ig is a moment of inertia with respect to the center of gravity. You can actually change Ig, find it with respect to a different point, and that case you have to use parallel axis theorem. We don't actually need to do this in our case. You just need to know the moment of inertia about the center of gravity. And alpha is the alpha that we were using actually earlier. Alpha is your angular acceleration, and it is actually a vector. In the case of planar motion, you can simply keep it like that. Now, if you want to find alpha, here's what you do. You need to actually write one more equation, and you need to sum the moments or the forces. The moment basically is definition of moment is actually equal to R cross F. And when you are basically finding the moment of a force, essentially you are multiplying the force times the distance, or R here is basically the perpendicular distance between the force and the axis that you are choosing. Let us try to do this. So here, that equation, you can actually apply it about any point on a rigid body. So when I sum the moments, I could actually sum the moment about the center of gravity, or I could actually sum the moments about any point. But the idea here is whatever that you do on this figure, you actually have to do on that figure. So if I sum the moment about the center of gravity, so here you are going to indicate that to me by this point, essentially an axis passing through the center of gravity, right? Not the point, but an axis perpendicular to the rigid body passing through that. And now you basically have to indicate the direction of the forces, right? So here, by putting this plus, I'm using my counterclockwise as my direction. So here, I'm summing the moment of these forces about point G, and what you are going to get. So I begin by the moment of the first force. How do you think the moment of the first force? So the moment, like I said, is basically you are going to take this perpendicular distance to the force, right? And I'm going to call this guy R1. So do you think R1 is going to be positive or negative in the way that I'm calculating its moment?
It's negative.
It's negative, exactly. Why negative? Because so G is my axis, so I'm summing the moment of these forces about this axis, perpendicular to the motion of the rigid body. Counterclockwise, so F1 is actually producing opposite motion to what I'm assuming. So the first moment of the first was going to be minus F1 multiplied by R1, right? Then the second force, F2, basically is going to be this guy, right? So you're going to take that perpendicular distance, right? All right, and this guy is going to be your R2. So again, this guy would actually be, is it positive or negative? It's minus, right? F2 times R2, and then the third force basically is gonna, you always like project that force, right? Almost make the line of the force infinite, and then draw a perpendicular distance, right? And then shortest distance will be your moment arm for that force, right? And F3, you will see it is basically positive. So plus F3 multiplied by R3. So these moments are equal to what? So because I'm summing the moments, now I actually have to go to this figure, right? So these are equal to, so if I'm summing the moments about this point, I actually only end up with IG alpha, right? IG alpha. And basically from here, I can actually get the angular acceleration of that rigid body. And then I can use kinematics to find the acceleration of point P. So the forces will give me the acceleration of this point A, and here basically I can actually get alpha, right? So alpha in this case is going to be minus F1 R1 minus divide by IG, and then we are going to look at IG in a second. So now you find your IG. Now I can actually find the acceleration of point P by saying that it is equal to AG plus alpha cross RP with respect to A minus omega square RP with respect to A, etc. Okay. So this is really the idea of this topic. Now, what do you think would happen if I sum the moment about this point P? If you sum the moments about this point P, you have to do the same thing over here, right? You basically obtain these radiuses again. But here, basically, you would still have IG, right? But actually, MA would actually begin to have a moment. So I would write IG alpha plus, I would actually add the moment of this inertial force, which is MA with respect to that point. So this is very important. So by doing that, basically you are doing the parallaxes theorem, which some of you might have learned in your high school. But this method will always work and will always, is very systematic, and you should apply this method. Again, if you sum down about this point, basically you have to use this, and the moment of this inertial acceleration will appear here, and again you'll be able to solve alpha. Once you have the angular acceleration of your rigid body, you can find the acceleration of any other point. Okay, so let me just cover the moment of inertia. What is IG? Let's look at IG right now. So the moment of inertia, right, or some people call it rotational mass. So IG is, by definition, is equal to R squared dm, and you integrate this guy from 0 to m, and there are tables basically for various rigid bodies. And in the case of a disk, let's say you have a disk, all right, and that disk basically could be rotating about different axes, right? So let's say this is my x-axis, let's say this is my y-axis, and this guy is my z-axis, right? So the rotational mass is defined by R squared dm. So Ix, if the disk is rotating about the center, then the moment of inertia of the disk will actually be equal to mr squared over 2. All right. If the disk is rotating about Iy or Iz, then the moment of inertia will be equal to mr squared over 4. These are basic stuff that you need to know. And then you can see that this is actually independent of the thickness, because the thickness of this guy, T, is related to the mass, right? So this could actually be a cylinder. So the moment of inertia of a cylinder rotating about its center will be equal to also mr squared over 12. All right. If you choose to rotate this guy about this point, then it would basically become like this, right? This is like, like a disk, right? So like this guy, right? So this guy could be, if you rotate this guy about this point, right? About this axis, basically, if it's rotating like that, then you are using this guy. But if it's rotating like this, then this guy is your moment of inertia. Some other objects that will appear with us is like a linear bar, right? And the linear bar, again, let us establish a quick frame here. Let's say this is my x, and then this is my y, and then z, and then notice this is always an orthogonal, like x, y, and then a z. In the case of this guy, Ix will actually be equal to 0 because you assume that this guy is doesn't have any radius. Iy would actually be equal to Iz because it doesn't matter if you are rotating this guy. And by the way, this is about the center, right? This guy is L, and this guy is L over 2. Iy is actually equal to Iz in this case is actually equal to ml squared over 12. Okay, if you now if you would actually here we're using this because this is the center of gravity. Okay, but if I actually want to calculate the moment of inertia about this point, does anyone know how we can calculate this moment of inertia about point O?
Over 3.
Over 3, yes, over. But how do you calculate that? Basically, you have to use parallel axis theorem, right? So if I have this is my y, let's say my y prime is here, like another reference. Iy prime is actually equal to Iy plus the parallel axis theorem, which is the mass multiplied by this length right there, right? L over 2 squared. So this is called the parallel axis theorem, where you can move this moment of inertia over to here. And I'm going to record the lecture basically where I solve how we actually get these because I want to jump in and then I want to do a problem on here before, or actually let us actually solve this very quickly. Let us actually do this and then do this analytically right now, and then we can go in and then solve the problem. How from this equation, how did I use this equation to actually get this I? Let's start by looking at the circle, right? Right, so let's say this is your disk, right? And the moment of inertia is actually equal to r squared dm, right? And this is integrated from 0 to m, where m is basically the mass of this disk. Okay, so first of all, yeah.
Sorry, بس ال dm مش ال change in يعني change in mass.
Yeah, it's an element. Yes, it's not a change in mass. Basically, you're okay. So what is the moment of inertia? Let us begin by finding what is the moment of inertia of. Let's say this is your axis of rotation. Let's say you actually have a point mass, right? What is the moment of inertia of this point, assuming this point is basically rotating about this axis?
mr squared.
Exactly, mr squared. Okay, so basically you are integrating this mass, and then basically because here the radius is constant, so here I of this tiny m is going to be equal to r squared 0 to m dm. Okay, this whole mass is basically at the same distance. So r squared is constant here. I'm going to put it here, and it will be r squared m in this case. Okay, if I'm looking at this guy. Now let's extrapolate this and assume all this mass basically is at the same radius, right? Let's say you actually have a radius of mass like a ring. What is the moment of inertia of a ring, do you think? So in that case, again, actually, I'm gonna actually, you want to start with that equation. So I is equal to, integrating this guy, r squared dm. So basically here, what I can do is basically, if I take like, an element like this, right? If I take this dm, right? In this case, this is my dm, and what I can do is I can say that dm is actually equal to, I can basically relate this dm to d theta, right? I can actually specify another angle theta here, and dm would actually be equal to r, right, multiplied by d theta. So r times d theta, right, is actually ds. Is the length of this tiny segment, right? So that would be your ds. ds is equal r d theta. So we're not done here, right? So r times ds is going to give me a length, and basically I need to multiply this guy by some density, right? So r times d theta is giving me ds, and so this is a unit length, and this is a density, and basically I would have to multiply it by, you know, the cross section of that ring. So that would be essentially here r a rho d theta, right? R is constant, A is constant, and then rho is constant in this case. So I would be equal to R square multiplied by dm, which is R A rho d theta. But in this case, basically, my variable is only d theta, right? So this is my rho. So here you are going to end up with basically r cube a rho, right? D theta, and you basically change this from 0 to 2 pi, okay? Because you are integrating over the whole disk. And that would be basically equal to r cube a 2 pi times rho. Okay, so now I can actually decompose that, okay? I can write r, right? R a 2 pi rho multiplied by r squared. In reality, this guy is actually the mass. Why is that? Because 2 pi r is what? 2 pi times r is the perimeter of this, okay? So the perimeter, I'm going to rearrange that. So 2 pi r, the perimeter multiplied by the area multiplied by the density multiplied by r squared. So 2 pi r is your perimeter. Perimeter multiplied by the area essentially give you the volume of this wire or the ring that is wrapped. So the volume times the density is going to be equal to the mass, okay? So, you know, here I basically made like a long way to come here, but you can quickly see that if you are in, the whole mass is at the same distance. So if you integrate r squared dm, you will always actually get r squared in this case. But let us actually now do this on the disk. So this is your disk, and let's call this guy x and then y, and I'm trying to do this I is equal to r squared dm. So I have to actually take a unit element. So what I'll do is, let's say you actually got a unit element which is a disk. Okay, so let's say this is your dm. Okay, I need to integrate this guy from 0 to the whole mass m, right? So here essentially now my radius is going to change, okay? So r squared, what is dm in this case? What is dm? How can I express that dm in terms of, you know, I have, this is my radius, and this guy is going to be equal to my dr, right? So here dm is that unit mass, okay? So I need to express this dm in terms of r. R can give me the volume, right? So again, it can give me the volume, and from the density of that material, I can basically get my, so I can express dm in terms of r, dr, and perhaps the density, right? So what do you think is the value of dm for this ring element? How can I get the mass from, what is the mass of this ring element? Can make some, you know, simplification. I can basically add some thickness to this. I think what we can see here is dm is going to be equal to what? So first of all, I want to get the volume of this guy, right? So this guy is a ring, right? It has a distance in this direction, right? And it actually has a depth, let's say t. In that case, basically, it's going to be equal to, well, first of all, we're going to get the perimeter of this guy, right? Which is 2 pi r 2 pi r will basically give me the length of this guy. 2 pi r, I have to multiply this guy by dr, right? So I'm multiplying this guy by the height of it. So 2 pi r multiplied by dr, essentially, you know, if dr is basically very small, you are getting that the perimeter multiplying this guy by dr is going to give you the surface area of this guy over here. And this guy has to be multiplied by the thickness, and again it has to be multiplied by rho. All right, there is another simplification of this. If you, let's say you don't know that you want to use this perimeter, I'm going to actually simplify it even further, and that is actually, let me draw it, you know, a little bit bigger so you guys can see what I'm doing here. So if this is my x and then this is my y, and let's say if I actually took this element right there, right, any element right there, okay, this is my dm element, and let's say this guy has a depth of t, right? So this guy has actually a depth of t. So I can say that this is my radius, right, to the center of this dm. I can actually define theta like that, right? If this is r, then what do you think the value of this guy right here? What is the value of this depth right there? I think this guy would be dr, right? This guy is going to be dr, and this guy from here to here is going to be r k times d theta, right? So if this guy is r, right, this guy is going to be r d theta. So this length right there is r d theta, and then this length right there is dr, right? So if I want to, what is the volume of this, like, you know, kind of like square element? So the value of this guy, dm is equal to what? Is equal to the density multiplied by the volume, right? So the mass of this guy is the density multiplied by the volume. So what is the volume? You know, the volume is the area multiplied by the depth, right? So T multiplied by the surface area of this element. All right. So rho multiplied by T. What is the surface area of this element? It is simply عندك dr on this end, and then you have r d theta on the other end. Right? You guys agree? So this can be treated as a square element, since it is infinitesimally small. So dA is going to be equal to dr multiplied by, so dr is the radial distance, and then r d theta is your transverse direction. So r multiplied by d theta. So I can rearrange these, and then I have rho t r dr and then d theta. So this is, you know, a unit element on this rigid body, right, as a variation of the radius of this rigid body, and then theta, it will change like that, right? So depending on your radius, right, you can actually, this is your differential element. So now if I want to actually get my moment of inertia, I have to integrate this guy with respect to r squared. So I is going to be equal to r squared dm from 0 to m. Now let us go on new paper. So here what we are going to say, so I is going to be equal to r squared multiplied by dm. So now notice dm actually has dr and then d theta as your variable, so you actually have to update that, right? And r squared multiplied by rho times t times r times dr times d theta, right? So now what is, can someone tell me what is the range of d theta in this case?
مش 0 to pi.
Exactly, 0 to 2 pi. How about r?
0 r.
0 to r, exactly. So you are integrating theta from 0 to 2 pi, so you are getting the whole mass and then the radius from 0 to r. All right. And here from now on, it's simple. So d theta, أول شيء you can integrate d theta لحالها, right? And by the way, essentially here you are doing, you know, the perimeter by integrating this d theta, right? So there is nothing here that is in function of theta except itself. So integration of, I can start either by doing theta or I can start by integrating r. And let me actually re-expand this a little further. 0 to 2 pi, you know that you have r squared and an r, okay? So it's going to be what? R3, right? R3, and then rho and t are constant, so I can actually bring them before the integral, right? So rho and t are constant, so r cubed dr d theta, and that is equal to 0 to r. Like I said, I can begin to integrate d theta alone. It will be 2 pi, right? R cubed dr. Now 2 pi is constant. I can bring it before, so I'm gonna end up with rho t 2 pi 0 to r cubed dr. Okay, now I can actually integrate that. And if I integrate r cubed rho t to pi, it's gonna be r4 to the power divided by 4. Okay, 0 to r, and then this guy is rho t to pi r4 over 4. Now, how can I show that this guy is actually equal to mr squared over 2? I can actually take the volume from here, okay? So I can actually calculate the actual mass of this rigid body. What is the actual mass of the rigid body? I can simply integrate the mass, right? If I want to get the total mass of that rigid body. So if I want to get the total mass, I can either integrate that, or I can simply realize that, right? If you can actually expand this here, I can actually write this rho t 2 pi r squared, and then this guy is multiplied by r squared. This guy is over 2, and then this guy is over 2. So here basically that 4, I'm separating it in 2. Why? Because I know that if I take these two here, I'm gonna end up with rho t pi r squared times r squared over 2. Do you guys agree that this is a mass? What is pi r squared? Pi r squared is what?
The
The
area.
area.
Area of the disk, right? Area of the disk multiplied by the thickness will give me what?
Volume.
Volume.
And multiplied by the density, it's going to give me the mass. Okay, so that is why.
كنا نستعمل البارامتر لا هلا عم نستعمل area.
Okay, because before we were just calculating the moment of inertia of a ring, right? And for the ring, basically, here I assume the density only, by the way, is here you actually have the area of the disk itself. Okay, so before basically you are simply using an element on the ring. Basically it is exactly the same. I'm not changing anything over here.
بس حتى بس جبنا دي ام بهيدا البروبلم ما استعملنا نحن البارامتر.
You mean this problem right here?
لا اللي عم نعمله هلا.
Yeah.
بس جبنا دي ام. Can you show us the formula?
Yes. So here basically when I got this, I came back and then I decomposed this into the mass, and because I knew the mass basically going to be equal to area times the volume. And by the way, the time is going to end, so guys log back in because we're going to save the recording. So this will end now. Okay, so if you want to get another way of doing that, basically you can integrate the mass, and here basically we replace whatever that we had for them earlier, and we are doing this double integral. We know the theta is alone. We don't have any other items that are a function of the theta, so I can do this alone, and I'm gonna get rho t times 2 pi and 0 to r. I have r dr, and that would be rho t 2 pi. This guy is r squared over 2, becomes r squared over 2 like that, and rho t pi r squared, right? Which is exactly what we did as this is your mass. All right. I'm gonna do one more example. Basically, let us do that of the bar, right? Why is the moment of inertia of a bar mr squared over 12? And maybe you guys can help me out with this one right now. So let's say this is my bar, right? And I'm trying to get the moment of inertia about this axis, right? Starting from the center. Okay, what I have to do is, let's say this is my element dm. All right, and let's say that the length of the bar is actually equal to L, and this is 0.0. Can someone help me out? How can I find the moment of inertia of this? I need to do r squared dm, and I need to go from 0 to m. How can I express dm here? How can I write this dm here? Well, obviously you need to know, let's say the density here is rho, and the cross section of this guy is a. So this distance right there is r. ما هيك إذا هيدا r, then هيدا رح يكون هون شو؟ dr, right? So what is the value of dm? So we said dm is going to be equal to
Rho A.
Rho A dr.
Rho A مظبوط multiplied by dr. Bravo, yes, exactly. Rho A times dr. And that's it, right? There is nothing to it. So I can basically just directly come here, right? So I'm going to end up r square rho A dr. But can you tell me how can I integrate that from 0 to m? So what should be the boundaries over here? Where should I integrate dr from?
0 to L over 2.
Exactly, 0 to L over 2, right? But how about the moment of inertia of this part? So if you did this, basically you are getting the moment of inertia of this part, right? How about here?
2 times.
Exactly, you can do 2 times, or you can do here minus L over 2.
بس دكتور ليه L over 2؟
Because you are integrating here, so you have this r squared dm. So here your goal is to evaluate this integration over the whole mass, right? So to do this, you start, so if you are integrating from 0, so r will vary from 0 to L over 2. This whole thing is L. So you integrate r from 0 to L over 2, but 0 to L over 2 will actually give you only half of it, right? You actually have to do all of it, so you can do actually minus L over 2. So you integrate from minus L over 2 to L over 2, this value, right?
okay.
And minus L over 2, so r square rho A dr. So I just like kind of, what is the integration? So rho A is constant, right? What is the integration of r square? It will be r cube over 3 ما هيك minus L over 2 to L over 2. What is the value for this? So I can basically multiply by 2 and then make the guy 0, right? So 2 over 3 rho A r cube 0 to L over 2. So basically I can multiply this by twice and then replace this guy by a 0. So that is going to be equal to 2 over 3 rho A. So it will be L cube ما هيك divided by 2 to the power 3, which is how much? 8, right? All right, so it is 2 rho A L cube over 24, right? But what is the mass of the bar, right? How can I get the mass of the bar? So 2 and 24 will actually be equal to 12, ما هيك? So rho A L cube divided by 12, and I believe that rho times A is rho times A times L is actually equal to the mass. ما هيك? Rho A L multiplied by L squared over 12, which is actually equal to ML squared over 12. And this is our answer. You guys agree with the process that we just did? Right, so this is the moment of inertia of a bar that is rotating about the center. All right, and this is the approach that we have to use. Basically, you express dm and then reintegrate that, and then this is how we found that moment of inertia. If you want to find the moment of inertia of the bar about this point here, basically you have to use parallel axis theorem, or you can reintegrate that starting from that point. Right, the easiest way over here would be to use parallel axis theorem. All right, and if I wanna, let me actually do this very quickly here. Let's call this guy here y prime. If I want to get I y prime is actually equal to I o plus m this guy squared, right? So L over 2 squared. So you can actually do this, and then you can get the moment of inertia about y prime. In our case, we never actually want to use parallel axis theorem because in the figure that I showed you at the beginning of the session, basically Ig is the moment of inertia of the center of gravity. So you never want to actually calculate the moment of inertia about any other point to calculate your analysis, right? Here we never actually needed to calculate the moment of inertia about any other point. So all you need is to calculate the moment of inertia about the center of gravity, and then you can use that moment of inertia about that point in your analysis. You don't actually need to map it over here if you are summing the torques about this point. Okay, guys, so that is it for this lecture. We have maybe about I think 3 more video lectures, and then we are going to be done. This year is obviously purely mathematical. Try to practice it, how you can get the moment of inertia on your own. And once we're done with this, next topic is basically we're going to start to relate the forces and the accelerations, just like what I showed you earlier. And you're going to see that all this is going to make perfect sense in a very simple and intuitive way. Any questions, guys, on this or on the course, or any questions that you have, you can just ask it right now.
Yes, doctor.
Yes.
مثلا بالاكزام we have to يعني نرجع نعمل البروسيس تنجيب المومنت اوف انرشيا او دغري نستعمل فورمولا.
دغري بتستعمل الفورمولا.
اوكي.
Okay, I'm just doing this for you guys to know where the equations come from, right? But you don't need to derive this. But you should be very familiar with how the equations apply. But I'll tell you on the exam, I won't be asking you this. And all links that you see in rigid body motions are maybe links like that. If it was a pendulum, for example, the top would be a link like that, the bottom would be a disc, right? And I won't be asking you. You'll see later on as you're doing this. Basically, you can decompose this into 2 rigid bodies, and then you have Ig alpha here, and then you have another Ig alpha here, right? And the moment of inertia will actually be the same. You don't need to do any parallel axis theory or anything like that. You just basically add them up.
Okay.
All right. Any questions, guys, or that's it?
That's it for me.
Okay. All right, guys. Thank you, and I'll see you guys Friday.
Okay, we have a lecture Friday, right?
Yes, there is a lecture on Friday. Yes.
Okay, thank you, doctor.
Okay, guys.
Thank you.
Okay, you're welcome. Bye bye.
هتردنا قدام التنين قبل الجمعة ما هيك؟
I'm sorry.
هناخد الإكزام اللي عملناه التنين قبل ال 8 May ما هيك؟
Yes, you will. Yes, I'll give you the results before then. Yes.
Okay, thank you.
Thank you, doctor. Bye.
You're welcome. Bye bye.